did this in the past, but this time we ensured that we have one exam where you are exposed to the sort of uncertainty with what concept apply. And so this is just going to be a continuation of what we did for the second exam. That is, given a problem in the exam, how do you figure out which concepts to apply? And then once you figure out the concept, you solve the problem. Okay. And so what I did was I took the same sheet which I circled earlier and I added. That was for particles. Now we have the entire syllabus, so it's going to be all chapters, all the 8 chapters, and I included all those things here. It doesn't change much, except that you'll have, there's a kinematics chapter. There are 2 chapters, 12 and 16, which is point 1, 2, 3, and so on. I just added those chapters. Okay, so since you know how to go about using this, I'll just start solving problems. What I did was I posted these questions on Blackboard, so they are without question numbers. Okay, that's really important because a question like that, you should be able to figure out what concept to apply, right? And so we'll go through the sheet to solve each and every problem today. And we'll basically do this for the whole of this week. And then I've not figured out what we're going to do next week. We still have 2 classes next week. So we can think about whether we want to have more of this or we want to do something else. Okay, so the 5-pound cylinder is falling from A with a speed of 10 feet per second onto the platform. Determine the maximum displacement of the platform caused by the collision. The spring has an unstretched length of 1.75 feet and is originally kept in compression by the 1 feet long cables attached to the platform. So these cables hold the spring in a compressed state. Normally, the spring is unstretched when the cables are not attached. It's at 1.75. Neglect the mass of the platform and spring and any energy lost during collision. So this is actually important. What it means is that if the platform had a mass, okay, if 2 masses collide, it's actually a sticking collision where the mass sticks to the platform, then there would be losses in collision. You cannot apply conservation of energy per se. You'll have to account for the fact that there's a collision and there's conservation of momentum. So the good thing is that since there's no collision, so to say, because one of the mass, that is the platform, is massless, you do not have to worry about that. Okay, so how do we solve this? Well, I'll go through this. First, step 1 through 4. First we figure out if this is a problem in kinematics only or dynamics. So kinematic problems do not need any information about Newton's laws or conservation of energy or work impulse momentum. So in this case, you're given the mass, and that's a good hint that this is probably not a pure kinematics problem. We go to the second point, which is if you're asked to find velocity when the object moves a certain distance, so number 2. So we know the velocity at A. We are asked to find the displacement, right? Maximum displacement. So how much would this platform compress? Let's call that X or Y. And so this actually fits number 2, which says that velocity is a function of distance, or velocity when the object moves a certain distance. Okay, so fits number 2. Within 2 there are 2 parts, 2A and 2B. The first part for 2A says if there are only conservative forces, springs and gravity, then apply conservation of energy, right? 2A. And 2B, if there are non-conservative forces, typically non-conservative forces are friction, external force, and so on. So this is only conservative forces problem because there's only gravity and there's spring. So I'm more inclined to use 2A. Okay. However, the book solves it using B. It uses principle of work energy. So I'm going to solve it using conservation of energy as per my handout. So first thing I do is use principle of conservation of energy. So again, you can only use this because there is no collision whatsoever. If I replace that platform with a mass, then you could not just apply conservation. You'll have to account for collision, use a momentum, but that's a different problem. I have a problem like this later on. Okay, so what we do is we try to relate. Well, let me write the equation for conservation of energy. It is T1 plus V1 equals T2 plus V2. Okay, and I'm free to choose what those 1 and 2 is. 1 would be instant when the mass is at A. So when the spring is compressed fully, that's going to be my instant 2. Let me draw with a different color. So this is for the maximum displacement y of the platform. And so now I can try to write the different expressions for T1, V1, and so on. So T1 is the initial kinetic energy. It's half mVA squared. Okay. So next is potential energy. Now there's a spring, there's a spring, and there is a gravity. Okay. For the gravity term, to find the potential due to gravity, I first need to define a datum about which I'm going to measure energy, right? So there are, as I said, it's independent of the datum. Your answer would not depend on the datum. To make your life easy, you can actually choose the datum to be either here or here. And the reason is, if you choose datum at 1 or 2, one of the expressions for potential due to gravity will be equal to 0. So let me just choose this to be the datum. Okay, which means that V2 due to gravity would be 0, but V1 due to G would not be equal to 0. It's going to be mass times gravity times the height from 1 all the way to this datum. So it's going to be 3 plus y. And what's about the sign? Is it positive or negative? Above the datum positive, below the datum negative. Okay, so that's the left hand side. Well, I forget something. I forgot the spring energy. The spring is compressed when the platform is there. So I need to write the energy due to the spring, which is half K times the stretch or the compression of the spring. So it's going to be the original length of the spring, the current length of the spring. The current length of the spring, which is when it is over here, is 1 minus the unstretched length of the spring, 1.75 squared. So it's always the current length minus the unstretched length, remember that, equals, by the way, what's the sign? Is it positive or negative? Potential is it negative? It's positive. So let's see. So work done is, I think it's positive, right? The way I remember this is work done and potential have the opposite sign. If you look at the work done, when you stretch the spring, the force is to the left, and a stretch spring, it's a free length, stretch it to the right, the force is to the left, but the stretch is to the right, so force times displacement is going to be negative, and so if work is negative, then potential is positive, so positive sign, equals, now I'm going to go to the right hand side, T2 plus V2. T2 is 0 because when the spring is fully compressed, the block is at 0 speed, plus potential due to gravity, V2 due to gravity, that's going to be 0 because right now the block is at the datum, plus the potential due to the spring. Now the spring, we need to find what's the potential energy when the platform is in this position. So that's going to be half k times, again, the current length of the spring minus the unstretched length of the spring. So the unstretched length is pretty simple. It's 1.75. We need to write the current length of the spring here. So that's going to be, let's see, so it's basically this length. And that length is going to be 1 minus y, right? Because this sum should be 1, and that's 1. So 1 minus y, and so this squared. Okay, so what remains is you put in the values for different things. Half mass is 5 divided by 32.2. Velocity is 10. Plus mg is 5. 3 plus y plus half k is 400 lb feet. Equals half times 400 times, that's going to be minus y minus 0.75 squared. One second. Okay, so when you try to expand this out, you will see that you will get a quadratic equation, and that will have two roots. One of the roots would be negative, which is not consistent. Y cannot be negative. We have defined it so that you take the positive roots, solve a quadratic equation. To get y equals 0.0735 feet. Okay, questions? 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 Okay, next question. Okay, there is an error in this problem. Basically, this is not 300, but this length is 300. Okay. And this is 200. Okay, let's read the question. So 40 kg disk is rotating with a speed of 100 radians per second when the force P is applied. So the force P is shown here. to brake as indicated by the graph. So the force P is not constant, it actually is something like this. A ramp followed by a constant. If the coefficient of kinetic friction at B is 0.3, determine the time t needed to stay the disk from rotating, that is, get the disk to come to a stop. Neglect the thickness of the brake. Okay, define the time needed for the speed to become 0. Okay, and we're given that initially the speed is 100 radians per second. Okay, so let's go back and go through this. Number 1 says, is it a kinematics problem? In this case, you're given the mass, and that's a good enough hint that it's not a kinematics problem. Okay, move on to 2. Number 2 on the sheet. If you're asked to find velocity when the object moves a certain distance, or vice versa. So in this case, that's not the case. You're not asked the angle turned by the disk. Third one says, if you're asked to find the velocity after a certain time or vice versa. So in this case, you're given the speed at time t equals 0. You're told to find the time when the speed is equal to 0. So that fits number 3. Okay, speed as a function of time. So 3 is what we've got to use. 3a is if there are external forces moments, use the principle of impulse momentum. If there are no external force momentum, then or the internal to the system, then use conservation of linear or angular momentum. In this case, if you look at the disk by itself, it's subjected to external force. One of the forces is friction force. There's also going to be a force P coming on the disk through the interaction of the disk with the brake pad. And so this is not 3B, but it's 3A. So there are external forces. Before I write down, well, there are two principles. There's a linear impulse momentum principle and there's an angular impulse momentum principle. So I need to figure out which of this principle I need to apply, or sometimes I need to apply both. Before I can write that down, let me just draw a free body diagram, and that will help me to identify what principle to apply. So here is a free body diagram. Okay, there's going to be reaction forces on the disk at O. We call that V and H. This is the brake pad. That's going to have also have forces. This we call that V A H A. There is P, which is shown there. There's going to be a force when the brake pad touches the disc. There's going to be a force of interaction. That's basically the normal force. Let's see. So the normal force okay, and since the disc is spinning clockwise, okay, the force which is going to stop it from spinning clockwise has to be inducing a counterclockwise torque, right? In other words, it's going to be this way. Mu k times n, so it's going to act in the opposite direction on the lever arm to break that. Okay, so I got to use one of the two principles, linear or angular impulse. Now, what I notice is that if I use linear impulse momentum, which is F equals mv, or impulse equals mass times velocity, then that equation would have these forces showing up no matter which free body diagram I use, right? HA and VA will figure in those equations, and I'm not interested in HA, VA. So I'm better off using principle of angular impulse momentum. And see where that takes us. So first I'll use angular impulse momentum for the lever arm. So use the principle of angular impulse momentum about point Okay, there is a slight issue. If I use the principle of angular impulse and momentum for the lever arm, that will not help me to solve for the time needed, because after all, what's happening is that the disk is slowing down. I want to use the principle of impulse momentum on the disk. So if I, that's O, so HO1 plus MO dt equals HO2. Right? That's the principle of angular impulse momentum for the disk. I couldn't use that for the lever arm because I'm interested in the slowing down of the disk and not the slowing down of the lever arm. The lever arm is not slowing down, so that's why I have to use that for the disk. So the initial momentum is I omega, let's call it 1 for the initial instant when it's rotating at 100 radians per second. Let's call this 1. So this is 2, this is 1, plus the net moment about point O. So you see that from the free body diagram that there are 4 forces on the disk. There is normal force, friction force mu k n, H and V. But if you take moments about O, then H and V will not appear in the equations because they are acting at O. N will not appear in the equations because N passes through O. So the only force contributing towards the net moment is mu k times N. So mu k times N dt, and I need to basically do the integral here. I think I'm forgetting an integral sign. Yeah. Equals the final momentum, which is 0. Now let me get the signs right. If I assume, well, omega is clockwise, so there should be a negative sign here because omega 1 is clockwise. My convention is counterclockwise positive, and I need to put a sign over here. I'm not sure if this is right. So if mu kn is acting to the left as shown, then you induce a counterclockwise torque. So this sign here is the right sign because the moment is counterclockwise, which is positive. So integral mu kn dt equals I omega 1 the inertia for a disk is mass times radius squared divided by 2 omega 1. So that all those things are known. Mu k is known. N is unknown. I do not know N. I'm given P, but not the normal force. So the next question is, can I somehow relate capital N with capital P. If I can do that, then I can use this plot to evaluate N, which will be a function of P dt. Let's call this 1. So let's figure out N in terms of P. So how will you figure out an expression for N, capital N, in terms of P, or the external force? How is N related to P? What will you do? Nobody?
Take the moment to take.
Take the moment to take. So you're given that the lever arm is massless, and so that helps, because now when you take moment about A equals 0, right? Because the lever arm does not rotate. So alpha is 0. Well, in this case, actually, the mass is given to be 0, so the inertia is going to be 0. So the moment about A is 0. When you take the moment about A, HA and VA, so this is looking at this Freebody diagram of the lever arm. P induces, well, P times 300 or 0.3 is going to be the moment due to force P. About point A, the moment is going to be clockwise. Right? P will turn the lever arm clockwise about A, so that's negative. N is acting upwards, as you can see, times 0.6, and that's going to induce a counterclockwise moment about A, that way, so positive. And then mu Kn acts at a distance of 200 or 0.2 meters, and that's going to induce about A, the force is this way, so it's going to induce a clockwise start, so negative. All this equals 0. So P times 0.3 plus 0.6 N minus mu K is 0.3, so 0.3, 0.2. So that equation involves only N and P, so you can find a relation between P and N. So what I'm going to do is solve N in terms of P. N comes out to be 0.55 P. So let's call that 2. So now I can now take equation 2 and sub that in equation 1. Okay, let me put in the values. So mu K is 0.3. The mass is 40 kilograms. The radius of the disk is 0.15. Omega 1 is 100. And so when you simplify this, you get integral P dt equals 1800. Where this integral, well, the limit actually is right from the time the force P is applied. The force P is applied from 0 seconds, so 0 to t. Okay, and the reason I wrote it that way is because I do not have an expression for P. I am given P in terms of a graph. The graph is here. Okay, so my goal now is to figure out what the time is such that P dt is equal to 1800. So is it here or it's here, right? And so what we'll do is integral P dt is the area under the plot. Area under plot. And so first find the area over here. So I'm going to guess that the time is somewhere here. And the way to check that is to first find the area under the triangle. That's half times half times 500 times 2. And you see that that's 500. Okay, and we want to, so integral P dt from 0 to 2 is 500. This is 500. So we want to find for what t that integral comes out to be 1800. So clearly that's more than this area. So it has to be, the time has to be somewhere here. So this area is area of a rectangle. Let me draw it in a different color. This area is height 500 times the width, which is t minus 2. Okay, so what I need is this should be equal to 500, which is the area of the triangle, plus 500 times t minus 2. So that sum of this triangle and the rectangle should be equal to 1800. Okay, so solve. So that's a single equation in a single unknown where t is the unknown, and you can solve for t. So solving that gives me t equals 4.6. Okay, is that clear? So that's probably one of the harder problems, which involves not just impulse momentum, which I did over here. I also had to invoke something from chapter 13, which was on F equals ma. In this case, torque equals I alpha, or m equals I alpha, where clearly the sum of moments equals 0, because in this case inertia is 0. Okay, so this is an example of a mixed concept problem. You can expect to see at least one or two questions which involve two concepts, and that's what makes it hard. It's not just these. So part of the question was applying this, which was principle of impulse momentum, but something in that equation, the first equation, was right here. We couldn't quite solve that equation by itself because one of the things unknown there was n, for which we had to go and apply the principle. Well, we had to apply F equals ma, m equals I alpha, or chapter 13 to solve it. Okay, any questions? Okay, so we have 10 more minutes. Let's do another problem. Okay, if bar AB has an angular velocity of 6 radians per second, that's shown here, determine the velocity of the slider block C at this instant. So we need to find the velocity of C. Okay, so this particular problem, we are not given the mass of the slider or of the linkage, and this is a kinematics problem. purely kinematic. You do not need to use F equals ma. Okay, there are two ways of solving a problem like this which involves velocities only. One is the relative velocity formula. The second method is instantaneous center. Yeah, I'm more inclined to solve it with the instantaneous center because it actually is, I would say it's much faster and much easier, at least to me, than solving it using the relative velocity formula, but that's a valid method. So let's use IC. Use IC. Okay, so first thing we do is we find the IC of link BC, and here is the way to do that. First find 2 points on link BC whose velocity direction is known, and those points are clearly C and B. Velocity of B is at right angles to link AB. Velocity of C is along the slot, as along the horizontal. Then draw normals to both those lines. So normal to C is this, and normal to the direction of velocity of B is always going to be along link AB. So the point of intersection is the IC. Okay. So before we identify the lengths, let's try to write a formula for the velocity of C, and based on the formula only try to find the distances we care about. So velocity of C is going to be, from the IC, is omega BC, or the angular velocity of BC, times the distance from C to IC. Okay, VC is unknown, which is what is asked. Omega BC is unknown, and CIC we can find that from trigonometry. So let's assume that we know that. So there are two unknowns, one equation, we can't solve it. Let's try to find the velocity of another point. In this case, its velocity of B is omega BC RB with respect to IC. Okay, omega BC is unknown, RBIC I can get that from trigonometry. I do not know velocity of B, but can I find velocity of B using the information omega AB? So it turns out that you can find VB very easily. It's basically omega AB times RB with respect to A. Right? That's the formula for velocity of B, because A is fixed, it's not moving. That's actually the IC formula, because A is actually the IC of link AB. So omega AB is 6. The length of link AB is it 200? That is 200. So 0.2. So 1.2 meters per second. Okay, so let me try to find CIC and BIC, and then I can solve VC. So let's try to find this length, this one and this one. Okay, so I know the length of BC, that's 500 millimeters. How can I find the other lengths. Let me try to find some of the angles. This angle seems to be 60 degrees because this is 90 degrees. Okay, if I can find another angle, then I'm good. If I can find one of the angles of the triangle. So this is 45. Can I find this angle? I think I should be able to get this angle. Okay, so if I extend this line, this is 30 degrees. So this angle here is going to be 180 minus 30 minus 45. What's that? 180 minus 75. 105 degrees. So this angle is 105. So this angle has to be 180 minus 105, so it's 75. Because this is a straight line, and so the angle swept by that line should be 180. So this is 75. So that's what I wanted. This is RCIC. This is RBIC. So I can use the sine rule. So RCIC divided by sine 75 equals RBIC. Sine of 60 degrees equals 0.5, which is length BC, divided by this angle, sine of this angle, so it's 75, 35, 45, I think. Sine of 45 degrees. From that I can find RCIC, comes out to be 0.6830, and RBIC comes out to be 0.6124. Okay, so what remains to be done is take 4 and 5, put it in equations 1 and 2, use 3 to find VB, and you can actually solve for VC. Okay, so that's it. Any questions on this? So what I suggest is next 4 questions in this handout, try to solve it yourself at home. Do not look at the notes. Try to solve it, try to get the final answer, and we can talk about it on Wednesday.
For the exam extra credits on Blackboard, it says like 2 points exam 2 and 2 points exam 3. So that means 2 points are added to each of them, or
so if you got 2 points, the bonus, right?
Yeah, I don't know. It says like exam 2, 3, 2 points.